Today I am going to solve one mass transfer problem based on absorption AB. A mixture of air containing 35 mole% ammonia is contacted with water containing 15 mole% ammonia in a single equilibrium contact stage. Assume that pure water is not evaporating and air is not condensing. If the total inlet vapor flow rate is 100 mole per hour and the outlet vapor contain 20 mole% ammonia, calculate the following. A. The outlet mole fraction of ammonia in the liquid, and B. The amount of inlet pure water in mole per hour. Now here is the absorption column. So liquid is coming in and liquid is coming out. Gas is coming in and gas is coming out. It is a counter current operation. So now first I am considering that liquid flow rate is L2 mole per hour and liquid out flow rate is L1 mole per hour. Similarly, here it is given that gas inlet flow rate is given, that is 100 mole per hour, that is given, and outlet we don't know, that is not given, G2, so mole per hour, that is gas outlet flow rate. Now here mole fraction at the inlet of the ammonia, that is given 35 mole%, so that is Y1 is 0.35, and Y2, that is outlet vapor content 20 mole% ammonia, so Y2 is given 0.20. Now X2, so that is inlet liquid containing 15 mole% ammonia, so X2 is given 0.15. So now X1 we don't know, so that we have to calculate. Now from here, so first, as these are the information we have, based on that we are going to calculate. Now here first Y1 is the molar ratio, that is Y1 by 1 minus Y1, so 0.35 by 1 minus 0.35, that is 0.54 moles of ammonia by moles of air. Next that Y2 mole fraction is given 0.020, so Y2 in molar ratio at 0.2, that is Y2 1 minus Y2, that is 0.20 1 minus 0.20, that is 0.25 moles of ammonia by moles of air. So that we are we calculated and got the molar ratio at 0.2. Now first we have to calculate the GS, means ammonia free air mole per hour. So that is nothing but G1 into 1 minus Y1. So that is, if I plug that Y1 value 0.35, so that will be G1 is 100 into 1 minus 3, Y1 means 1 minus 0.35, so that is 65 mole per hour. So that is ammonia free air mole per hour. So that will be fixed. Okay, inlet and outlet. So GS at the outlet, ammonia free air mole per hour, that is 65 mole per hour. Now X2, now here that molar ratio, the moles of ammonia by moles of water, that we can calculate from mole fraction 0.15. So 0.15 by 1 minus 0.15, that is 0.18. Now here X1 we don't know because that is not given, we have to calculate. Now after getting that information, so we have the equilibrium data. Here one thing still remaining, LS is the pure water, pure solvent mole per hour, so that will not change, so that will be as it is at the inlet and outlet. After getting that information, so these are the information we have, and we have that equilibrium data. From that we can easily calculate that X1 means moles of ammonia by moles of water. So now here that at X2 Y2 we know. So first we have to do the mole balance of ammonia. NH3 in the gas phase inlet, NH3 in liquid phase inlet. So NH3 in gas phase outlet, NH3 liquid phase. So if I do that, so here first we have to plot that. So that is Y2 0.25 and X2, that is 0.18. So that is the point, one point. Another point Y1 0.54. So that will cut the equilibrium line, this point, and from there I can draw that vertical line. So from here we will get X1 is 0.27. So now here mole balance is we already know, and then so as we got that X1 is 0.27, so 0.27 moles of ammonia by moles of water. Now here, if I do that, if I write the mole valence of ammonia, so that is Gs into Y1 plus Ls into X2. That Gs is the ammonia free air and Ls is the ammonia free pure solvent. Ammonia free solvent, that is pure solvent. And Y1 is that mole ratio of that ammonia by air, and X2 is ammonia by water. So Gs into Y1 plus Ls into X2, that is the inlet, and Gs into Y2 plus Ls into X1. So now here, if I this is the things, if I reorganize, we will get, all the data are known. So Gs we know 65, Y1, Y2 we know, Ls we don't know, that is the that pure solvent flow rate, Ls 0.27 minus 0.18. So after plugging everything, so Ls will get 209.4 mole per hour. Now NH3 in liquid phase, that outlet mole fraction is that, as we know x1 molar ratio, so we can easily calculate mole fraction, that is x1 1 plus x1. So 0.27 by 1 plus 0.27, so that is 0.2125, that is the mole fraction. So here that outlet mole fraction of the ammonia in the liquid, so that is here, this is the answer A, and this is the pure water flow rate, so that is B answer. That's it. Thank you.